The atmospheric compositions of distant exoplanets light years away, the JWST has become a sentinel of cosmic discovery. Among its most recent and astonishing revelations is the observation of a cataclysmic event involving Neptune, the most distant of our solar system's 8 planets. The telescope captured something extraordinary. A massive object colliding with the ice giant, sending shock waves through the scientific community and prompting new questions about the dynamics still at play in the farthest reaches of our celestial neighborhood. This single observation has not only redefined our perspective of Neptune, but has also expanded the boundaries of what scientists believed possible in the cold outer rim of the solar system. Neptune, named after the Roman god of the sea, has long captivated astronomers with its rich blue coloration, mysterious atmosphere, and extreme weather systems. Located approximately 4.5 billion kilometers from the Sun, Neptune is a remote frozen world often cloaked in darkness and largely hidden from direct observation. Its remote location makes it one of the most enigmatic planets, a giant shrouded in icy mysteries. Prior to the JWST, our most detailed understanding of Neptune came from the Voyager 2 flyby in 1989, which offered only a fleeting glimpse of its strange beauty. That brief encounter revealed hints of Neptune's turbulence, its rings, and the dynamic nature of its largest moon, Triton, yet it left countless unanswered questions. But now, thanks to the capabilities of JWST, scientists are witnessing the dynamic processes of this distant world in stunning detail. What was once only a pale blue dot blurred by distance is now being dissected layer by layer in infrared wavelengths. Neptune's supersonic winds, which can reach speeds of up to 2,000 km per hour, are unlike anything on Earth. Its immense rotating storms and its faint ring system have long intrigued planetary scientists. The sheer power of Neptune's atmosphere, where winds break the sound barrier and massive dark vortices swirl across the planet's face, has always suggested a world of chaos beneath its calm azure glow. However, this latest discovery, a high-energy impact event, has opened entirely new avenues for understanding not only Neptune but also the structure and evolution of the outer solar system. It was the kind of discovery that happens only once in a generation, a natural cosmic experiment that allows planetary scientists to study processes in real time rather than speculate through models. The event was first noted when astronomers studying JWST's infrared data noticed a peculiar and unprecedented anomaly in Neptune's upper atmosphere. A sudden burst of heat and energy disturbed the planet's otherwise frigid equilibrium. What initially appeared to be an unexplained fluctuation soon gained clarity when the telescope's imaging systems captured a distinct bright infrared flash. The source of the disturbance appeared to be a massive object, a large asteroid, a giant comet, or possibly even a rogue planet, that had violently slammed into Neptune. The collision sent an enormous shock wave through the planet's thick gaseous atmosphere, creating visible thermal disturbances and a brief but detectable flash of light. That tiny glimmer, invisible to the human eye, became a beacon of discovery in the realm of infrared astronomy. Although the exact dimensions of the impactor remain uncertain, preliminary calculations suggest it may have been several kilometers wide, similar in scale to some of the largest known asteroids or the icy nuclei of long-period comets. Such an impact is exceedingly rare, especially in the far reaches of the solar system, where planetary orbits tend to be stable and relatively free of the debris and gravitational chaos more typical of the inner solar system. That this object struck Neptune at all suggests it may have been pulled in by the planet's gravity from the Kuiper belt, or even more intriguingly, from the Oort cloud, a hypothetical distant spherical shell of icy bodies that surrounds the solar system. Another tantalizing possibility is that the impactor was a rogue planet, a planetary body ejected from its original star system that drifted through interstellar space until it was caught in Neptune's gravitational grasp. Rogue planets are cosmic wanderers, expelled from their suns in the early chaos of planetary formation, and their existence remains one of the great mysteries of galactic astronomy. To think that one of these free-floating worlds may have ended its journey by colliding with Neptune is as chilling as it is awe-inspiring. Throughout Earth's own history, collisions with large celestial objects have had dramatic consequences, including the asteroid that likely caused the extinction of the dinosaurs. Other planets, such as Jupiter, have experienced similar impacts, most famously the Shoemaker-Levy 9 collision in 1994. But for Neptune, a planet on the outermost edge of the solar system, this kind of cosmic violence has never before been observed with such clarity. The sheer remoteness of Neptune has always rendered it a world just out of reach, and yet the JWST has now brought its drama into sharp focus. The implications of this collision are wide-ranging. The massive energy released by the impact likely altered Neptune's atmosphere, which is composed mainly of hydrogen, helium, and methane. The shock wave would have instantly vaporized vast amounts of gas at the site of impact, generating atmospheric turbulence that could persist for years, if not decades. Given Neptune's already extreme weather conditions, the infusion of new energy may intensify storm systems or give rise to entirely new atmospheric phenomena. Cyclones larger than Earth could spin to life, their roots nourished by the collision's disruptive energy. The impact may have also disturbed Neptune's faint rings, which consist of tiny dust particles and are not well understood. Unlike the structured and reflective rings of Saturn, Neptune's rings are dim and diffuse. The force of the impact may have ejected additional material into orbit or disrupted the paths of existing particles, causing changes that could shed light on the origin, evolution, and stability of planetary ring systems across the solar system. For decades, planetary scientists have debated whether Neptune's rings were remnants of shattered moons or relics of primordial formation. Now, with the rings potentially stirred by the collision, scientists have a chance to study them anew. Triton, Neptune's largest and most enigmatic moon, may also have been affected by this colossal event. Triton orbits Neptune in a retrograde direction, a rare feature that suggests it was not formed alongside Neptune but instead captured by the planet's gravity long ago, likely originating from the Kuiper belt. Triton is among the most geologically active moons in the solar system, with cryovolcanoes that vent nitrogen gas and icy particles into space. The seismic energy from the Neptune impact may have triggered tectonic shifts or intensified cryovolcanic eruptions on Triton. Should this prove true, it would offer an extraordinary opportunity to study the moon's subsurface composition, internal heat sources, and its potential to host a subsurface ocean, a key requirement for life as we know it. If the collision was not an isolated event, but part of a larger pattern, it may necessitate a re-evaluation of the gravitational dynamics and object migration pathways in the outer solar system. It could imply the presence of more large bodies in eccentric or unstable orbits, possibly posing future threats not only to Neptune but also to the inner planets, including Earth. A single event like this expands the map of risk in the cosmic landscape. Suddenly, the serene outer solar system looks less stable, more unpredictable, and alive with hidden forces at work. JWST's role in capturing this momentous event cannot be overstated. Launched in December 2021 as the successor to the Hubble Space Telescope, the JWST specializes in infrared astronomy and is optimized for detecting subtle thermal signatures in cold and distant regions of space. Capturing this collision in near real time illustrates both the telescope's technical capabilities and its power to reveal the ever-changing nature of planetary environments. More than just an observatory, JWST has become a time machine, showing us processes in motion that shape planetary histories across billions of years. In the coming months and years, scientists will continue to monitor Neptune, observing changes in its atmosphere, tracking any alterations to its rings, and scrutinizing Triton for signs of increased geological activity. The event also serves as a valuable analog for studying exoplanets, particularly gas giants that exhibit strange atmospheric or thermal characteristics. By comparing Neptune's behavior after the impact to data from other planetary systems, astronomers can refine their understanding of how exoplanets might respond to similar events. Additionally, this dramatic development could rejuvenate interest in launching a dedicated Neptune orbiter, a long-desired mission that could probe the planet's internal structure, atmospheric dynamics, and complex moon system with far greater precision. No spacecraft has visited Neptune since Voyager 2, and a return mission could yield a treasure trove of new insights, especially in the aftermath of such a transformative impact. Some researchers have even proposed sending a lander to Triton, which may now be experiencing increased geological activity. If Triton's internal heat levels have been elevated by the energy transmitted through the Neptune system, its potential subsurface ocean may become more dynamic, improving the chances of detecting life-supporting chemical processes or even microbial life. Studying Triton's response could also improve our understanding of the nature of captured moons and how their interactions with host planets shape their long-term evolution. The identity and origin of the impactor is perhaps the most intriguing mystery of all. If the object originated in the Oort cloud, this would mark the first confirmed observation of an Oort cloud body striking a planet, a historic milestone for solar system science. Debris from the impact might contain pristine material from the early solar system, preserved for billions of years in the icy outer regions of space. Alternatively, if a rogue planet was responsible, the implications become even more profound. Rogue planets are thought to be common throughout the galaxy, cast out of their home systems during the chaotic early stages of planetary formation. A documented interaction between a rogue planet and one of our solar system's members would mark a significant event in the study of planetary dynamics and interstellar phenomena. In this context, Neptune's collision becomes more than just a cosmic spectacle. It becomes a gateway into understanding the ancient history and continuing evolution of our solar system and others beyond it. The JWST has revealed that even in the cold, dim outskirts of our own star system, dramatic and transformative events still unfold. These are not mere footnotes in planetary history. They are pivotal chapters full of data and discovery that help scientists unravel the complex forces that shape celestial bodies. As data from the James Webb Space Telescope continues to stream in, offering deeper insights into this extraordinary collision, the astronomy community finds itself at the cusp of profound revelations, not just about Neptune, but about the grand design of planetary systems, the risks and wonders of cosmic collisions, and the tantalizing possibility that life-supporting environments might exist in the most unexpected corners of our solar system. Future missions could capitalize on this remarkable cosmic incident by keeping a close watch on Neptune's atmosphere, its ring system, and especially the surface and geological activity of Triton. Scientists are particularly interested in monitoring for surface changes, cryovolcanic eruptions, or shifts in orbital dynamics that could have been triggered by the immense energy released during the impact. These after effects are not merely curiosities. They represent critical data points that could lead to transformative insights about how outer solar system bodies respond to extreme events. As the James Webb Space Telescope continues to send back infrared images and spectral data, researchers will be able to track the progression of atmospheric turbulence across Neptune's surface, observe any evolving